When high-energy cosmic events like supernovae occur, they release cosmic rays, high-energy particles traveling at relativistic speeds. If these rays collide with the atoms in the atmosphere, the force from the collision releases a shower of subatomic particles.
There are many kinds of particles that will result from this collision, and this muon is just one of them. It has almost the same properties as an electron, except it's 200 times the mass and pretty unstable, decaying after just 2.2 microseconds on average.
Now, only the fastest muons can reach the Earth before this decay happens, but as soon as they enter electric fields, they start to slow down. Since opposites attract, when these negatively charged particles get close enough to the positive charges found in the nuclei of atoms, they can get pulled and slowed down,
Releasing a type of electromagnetic radiation called Bremsstrahlung that increases as more and more kinetic energy is stolen by the atoms. Even though muons and electrons have the same charge, muons have a larger mass, so it's harder for the atoms to hold them, meaning they don't produce as much Bremsstrahlung, thus conserving more energy. And it's this conserved energy that allows muons to penetrate deep into matter, deeper than X-rays or even gamma rays, creating a new imaging technique called muography.
Similar to how the sun would cast a shadow if its rays were blocked, muons cast shadows too, in the forms of 3D images called muograms. When muons pass through an object, some of them may get blocked, but by calculating the trajectory of the ones that do make it through, we can generate these 3D images, these shadows. These shadows tell us everything from the density to the volume of an object, and by observing them, they give us clues on what the object must have been without us having to see it. Scientists at the Scan Pyramid project were able to take advantage of this technology when they placed 2 muon detectors near the Great Pyramid of Giza. They detected a strange influx of cosmic ray muons, discovering a secret room near the Queen's Chamber. Since muography works by giving us 3D images, we also found a way to explore the ancient world in a way that could still preserve it. All thanks to these cosmic ray muons.
Now remember, these cosmic ray muons are the result of the nuclear interactions between the atmosphere and cosmic rays, so there's no reason to believe that these same interactions don't happen on other planets as well. Taking advantage of these interactions on Mars could help us tackle long unanswered questions, with perhaps the most important pertaining to life. However, the environmental conditions make it near impossible for life to be sustained, but so far we've been limited to only what's visible, and it's logical that we just need to dig deeper. Scientists believe that there are areas underground where liquid water lie. These underground areas would be less dense than their surroundings, but by calculating the muons when they pass through them, we could find these potential sources of water. And where there's water, there's life. Since water is such a basic necessity for all life, this could bring us one step closer to verifying sustained life forms on Mars, and even closer to retaining a future that's been envisioned by many. With muography, we have a vision that allows us to see beyond the barriers that lie ahead of us. Envisioning the future is one thing, but getting there would take something as simple yet revolutionary as another discovery. Thank you.